So, what we proved fairly successfully, I think, is that first order predicate calculus and actually the Hilbert style system is complete. We have proved the resolution method is also complete, we have proved the tableau method is also complete. And since essentially the natural deduction system can also be derived from the Hilbert style system with that extra existential elimination rule and so on and so forth. So, the natural deduction system is also complete. I mean, so that's so we don't even need to bother about proving the completeness of that natural deduction system. So, and especially since we showed that even though the existential elimination is not a derived rule of the Hilbert style system, every proof which involves that can also be converted into one which does not use existential elimination. So, adding that existential elimination as a proof rule does not make your system inconsistent. That's the first thing. The second thing is that it's still complete. Yeah. Okay. So, the natural deductions. So, Genson's natural deduction system is also complete. So, and the tableau methods are also complete. So, now what it means therefore is that any logical theory, any mathematical theory you build on top of first order predicate calculus is essentially a first order theory. Yeah, and we will see that we will see the meaning of that. So, there is this first of all there is a limitation of expressibility in first order, which I will not expressiveness properties, which I will not go into. So, as far as the first order theory is concerned, its incompleteness therefore depends entirely on its axiomatization and does not depend upon any incompleteness of reasoning within first order predicate calculus. So, what we are essentially saying is that the reasoning mechanisms of first order predicate calculus are complete and they are consistent. So, any incompleteness that you see in a theory, in a first order theory, is essentially due to the axioms that you what are called the non-logical axioms that you introduce as part of the theory. So, let us just look at some first order theories. So, when I go through these examples, you will also be you should be able to connect it up to whatever you have already done in these theories and see the differences also, right. So, for example, so let's start with this. Actually, the simplest first order theory is the theory of directed graphs. Let us say, yeah. What does it have? The theory of directed graphs, in its most fundamental form, has absolutely in its signature it has just one edge relation, that is it, a directed edge relation, there is nothing else to it. Now, that is what I am calling E here. Okay. It does not have any operators and your carrier set is usually a set of nodes, but that is like the model, right. I mean that is like the structure, that is going to be brown in color if you like. Yeah. But otherwise the only relation you have is the directed edge relation, right. And in general the only axiom you have is that the edge relation is irreflexive. I mean, if you are talking about simple directed graphs, yeah. Normally when we are talking about directed graphs in graph theory, they mean simple directed graphs. So, therefore, there are no self loops on the nodes, right. If there are no self loops on the nodes, then essentially your edge relation is irreflexive. Okay. There could be cycles, of course, but then those cycles have a length of at least 2, right. I mean, so there it just this irreflexivity just says that there are no self loops on nodes. So, there are no length 1 cycles. Okay. And so, essentially what you can derive from here is almost nothing. But then you go back to what you studied about directed graphs in, let us say, your discrete math course or some such thing, you will find that all those theorems that you had about simple directed graphs, they involved counting. Basically, this simple axiom with all the with whatever first order logic axioms, first order predicate calculus axioms and inference rules, you can derive very little. You will not be able to get any interesting theory at all. The interesting aspects start with, for example, counting. One saying, one which says that the number of in degrees in a directed graph should be equal to the number of out degrees, for example, right. The degree of a node, the in degree of a node, the out degree of a node, they are automatically they bring in the integers or at least the naturals. Okay. So, in fact, if you see, so the first order theory of directed graphs viewed in isolation as simply an edge relation gives you almost nothing. It gives you just essentially whatever you can derive from irreflexivity and the axioms of predicate calculus, the proof rules of predicate calculus, there is nothing else, and that is not very interesting. The interesting things really come from certain combinatorial aspects. Yeah. Okay. So, so in that sense this is too trivial. I mean looking at this first order theory is not very interesting. Okay. From directed graphs, of course, we can go to the next thing, undirected graphs. So, essentially what you have is a signature. Again, the signature has only an edge relation, nothing else. By the way, you could have an equality relation. So, very often I am not going to mention the equality relation. If there is some strange proof in which especially you want to say that two different nodes which for purposes you called some nodes with different names for purposes of argument and then proved that they are the same node, that would constitute an equality relation. So, I am not mentioning equality here, but in general what we are asking for is actually a first order predicate calculus with equality always. That without that the theory will become even less interesting than it would be. Yeah. Okay. So, in the case of undirected graphs, for example, you also have, in addition to, you have the edge relation which is irreflexive, of course. Again, we are talking about simple undirected graphs. So, it is irreflexive, however, there is symmetry. That's what you want about the edge relation. But normally in any discrete math book, for undirected graphs, the edge relation is not really thought of as a relation, but it is thought of as a set of two element sets in order to emphasize the undirectedness. But that is but then that will take us to axiomatic set theory and so on and so forth. Those are complications which we do not require at the moment. So, the first order theory of undirected graphs essentially says that you have an edge relation which is symmetric, and that is sufficient. And in fact, most of the time when we draw undirected graphs, we essentially think of it as essentially a symmetric relation. Yeah. Okay. So, the interesting thing here, of course, is that you can take this symmetry axiom to be either a directed implication like this or a bicondition like this, and there is an exercise which shows that they are both equivalent as far as first order predicate logic is concerned. But remember what that means. It means that where is this? Problem 12, yeah, here. For any binary predicate psi for all xy, psi of xy arrow psi of yx is logically equivalent to for all xy, psi of xy is biconditional psi of yx, right. Note that this logical equivalence does not mean that the corresponding biconditional is a tautology. Okay. It is not a tautology. We have defined what a tautology is, because this equivalence cannot be derived only from the propositional axioms and modus ponens. It requires universal elimination, instantiation of the variables x and y, and then again generalization. So, it is not a tautology, but it is logically valid. Yeah, so, the corresponding biconditional is logically valid, but is not a tautology. So, that is what you get in your. 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 So, theory of directed graphs, yeah, undirected graphs, yeah. Okay, so this is all. So basically, from a purely logical point of view, there again in the theory of undirected graphs, most of the interesting theorems had to do with counting, combinatorics, and so on and so forth. I mean, which means that what you are actually doing is you are actually, it means essentially you are imposing a structure. The stratification I spoke about is essentially that you have your first order logic axioms here, let us say H1, and then you have essentially number theory, okay. And many of the interesting results actually come from combinatorics, which is essentially number theory. And then you actually have your theory of undirected graphs or directed graphs on top of this. I mean, so basically one of the things that we implicitly assume are facts from number theory in our theory. So whatever you learn, let us say in discrete maths on directed or undirected graphs, essentially has a stratification of this form, yeah. So otherwise the theory would be quite uninteresting, and there is very little you can actually prove. Okay. So that is what the theory of undirected graphs is. Okay. Now since we were on relations, there is this theory of irreflexive partial orders. By the way, I use terms, most of the other books have confused me for many years with their terms. So I am actually using some explicit terms which may not be found in books. So when I say, I mean the notion of, they use notions like strictness or total, and the word total is a very ambiguous word for various reasons. Totality of a relation is different from totality of an order, and so on and so forth. So I am using what I consider to be precise and unambiguous terminology for these things. So the usual less than relation on any structure is an irreflexive relation, and it could be a partial ordering or a total ordering. Just as the word total is ambiguous, the word partial is also ambiguous. Okay, so we have to be very careful how we use these words. Okay, so let's think of this. So I am just so there is a single relation. It is irreflexive and it is transitive. In that sense, it is different from the edge relation in directed graphs. Yeah. However, however, supposing you take the transitive closure of the edge relation in directed graphs. Yeah. So then essentially that the transitive, if you take that as your signature rather than the edge relation itself, then the theory you get is the theory of irreflexive partial orders, right. I mean, so that's so this kind of, so what actually logic allows you to do is to do this clear stratification and clearly compartmentalize things, what goes where, yeah, and and it allows you to formalize these things there. Therefore, so essentially what we are saying is, whatever is there in the theory of irreflexive partial orderings is just the theory of directed graphs, that is it, the theory of paths in directed graphs. Yeah. So if you replace the edge relation by the path relation, that is it, what you have is an irreflexive partial order. Yeah. Of course, there is a question of things being acyclic. So if there are cycles in the directed graph, then this goes beyond that. Okay. So we'll come to that we will come to that at some point, but in some indirect fashion. I am not going to be directly interested in that. Yeah. Okay. Then you have irreflexive linear orderings. So this is, so very often many books call this total orderings, and then very often they do not specify whether the total ordering is strict or not strict. So there is a difference between the less than and the less than or equal to. The less than is an irreflexive relation, the less than or equal to is a reflexive relation, and in between irreflexivity and reflexivity you have a lot of stuff. you have things which are neither irreflexive nor reflexive. You have relations which are, which could be, which essentially there is at least one element x such that x is related to itself, and there is at least one element x such that x is not related to itself. So, all those kinds of orderings that you can get lie between irreflexivity and reflexivity, and that is usually a matter of confusion very often in if you, when you do not formalize the theory in a precise fashion. Yeah. So, the notion of irreflexive linear orderings is essentially this. Yeah. So, all you have is a less than relation which is irreflexive. So, for there does not exist any x such that x is less than x. Okay, that is the and this that is a logical equivalent of this irreflexivity. There is transitivity, okay, as we had in the case of irreflexive partial order. Yeah. So, if essentially A is less than B and B is less than C, then A is less than C. That is what the transitivity says. And how does how do irreflexive partial orderings differ from irreflexive linear orderings? There is a trichotomy law in the case of a linear order, which is essentially to say, okay, I mean I am calling this trichotomy. Here again books can vary in various ways, but given any two elements x and y, there are exactly three possible relations between them. So, one possibility is that x is the same as y. I mean, for purposes of argument I have considered arbitrary x and y, but they could be the same element. So, if they are not the same, then either x is less than y or y is less than x. So, that is, so this trichotomy is what makes the difference between irreflexive partial orderings and irreflexive linear orderings, or irreflexive total orderings as we call them. The notion of a well ordering essentially is that of an irreflexive linear ordering which is bounded below, right, well orderings. In fact, if you think of it carefully, all the proofs that you did using structural induction or using the principle of mathematical induction, they can all be generalized to essentially proofs saying that there is a well ordered structure, there is an irreflexive linear ordering which preserves that property. You just go back to all those proofs, essentially they are bounded below. In the case of structural induction, the bound below is the basis. In the case of any induction, the bound below is the basis that you use, and it might be unbounded in the other direction. Okay. So, and in the case of structural induction, actually what you are using is an irreflexive partial ordering, but what you also use is a particular path, a linear path in that partial ordering, which anyway is bounded below, okay, which has a least element, right. So, what your actual well orderings can be generalized to irreflexive partial orderings, because I can consider each individual path of the partial ordering to be a well ordering, to be a linear well ordering in itself. Yeah. So, okay, so that is the theory of irreflexive linear orderings, and then of course you have the notion of reflexive. So, this is the notion of a preorder, and I will implicitly assume that a preorder is reflexive. These in many books are also called quasi orders. Some books distinguish between preorders and quasi orders. Some of them say one of them is linear, one of them is irreflexive. I mean, the confusion is total, yeah, but but the most precise way of looking at it is through these axioms. You have a reflexive relation and you also have a transitive relation, and that is a priori. So, the theory of, so all your usual less than or equal to relations are essentially those of reflexive preorders. Yeah. Okay, but what you study more often in your discrete math courses is that of reflexive partial orderings, where there is an extra property of antisymmetry. Okay. This antisymmetry, a source of much mental trauma to students, is really this question of identity of objects which have two different aliases. So, this, if we are considering first order predicate calculus with equality, however, that equality is such that syntactically distinct terms are considered different. Okay. And when you say that x is less than or equal to y and y is less than or equal to x, implies x is equal to y, what you are actually saying is that x and y are the same object. I mean, they are just, we have just given them aliases, given that same object two different aliases, that is it, right. And so, this antisymmetry property, which essentially identifies objects which might have more than one name, is what this is what gives you a partial ordering. Yeah. So, partial ordering, of course, so and I will assume that by partial ordering we mean a reflexive partial ordering. Yeah. Okay. So, there is a reflexivity axiom there, and there is transitivity and there is antisymmetry, and of course, so the theory of, so this phi PO, so in each case this capital phi with a subscript is the set of all axioms which just define the theory. So, all the logical consequences of this along with the axioms of first order predicate calculus constitute the first order theory. All the logical consequences constitute the first order theory of this structure. Yeah. Okay. But these things are not so. So, then you have reflexive linear orderings. Remember here that if it is reflexive, then you actually have a dichotomy law, not a trichotomy law, because I mean that is sufficient, that is what I am trying to say. Yeah, I mean I do not need a trichotomy law. Yeah. Okay. So, I have a dichotomy law for less than or equal to. Yeah. So, that is my notion of a reflexive linear ordering. Okay. Now, well, then you have equivalence relations, which are reflexive, symmetric and transitive, and here I mean that is what I am saying. So, here is where it is yeah. So, here is where so notice that this equivalence is something that might be defined external to the set of objects. So, if x and z are equivalent, that does not mean that they are the same object, right. So, you should not confuse it with the antisymmetry in the partial ordering case. Yeah. Okay. So, that is why I have used a different symbol for this, but what does happen normally in algebra is, if you quotient out the structure on an equivalence relation, then what you are actually dealing with, the objects that you are dealing with are equivalence classes. So, if you, when you talk about an object A, you are essentially talking about the set of all objects which are equivalent to A by your equivalence relation, and therefore, if you are first, so then what you are dealing with on the quotiented structure, the first order theory of that quotiented structure actually has the antisymmetry property. If A and B are equivalent, then their equivalence classes are exactly the same class, they are the same object, right. So, the theory of equivalence relations automatically takes you also back to allows you to map between between the theory of using just allows you to map between just the first order predicate calculus with equality on the quotiented structures and separately as the first order theory of equivalences. Yeah, so that's okay. Now, so this is some these are some examples of first order structures, and what we normally do is we just whenever we are talking about a theory in computer science, logic, mathematics or anything, we just give these defining axioms, that is it. We just say that okay, a relation is an equivalence relation if it satisfies these axioms, and most often we do not even use the we do not even put the universal quantifier, because we know that validity is preserved only under universal closure. Yeah, right. So, the universal closure is implicit, and this is how we work with it. So, let us in order to do something concrete, I thought we will start with Peano's postulates and the theory of numbers. We will just do some basics of the formal what is known as formal number theory. Sometimes it is also known as formal Peano arithmetic, but there are subsets of it also which are interesting. So, from decidability point of view, but I will not get into that, but just let us look at this. These are Peano's postulates, which essentially, so the first, so if you have studied Peano's postulates somewhere in school or whatever, you will see that it has basically five postulates, where the first two postulates, 0 is a natural number and if x is a natural number, okay, I am using this plus 1 as the successor function. Usually s is used, but since I am using s for that defining sorts and so on and so forth as a symbol for sorts, I am using plus 1, which I think intuitively is fine. So, it is called the successor of x. Okay, so, this P1 and P2 essentially define the signature. They essentially state that there is a distinguished constant element called 0 and there is a unary function called successor, and they basically, these postulates do not do anything other than define the signature. In programming terms, it is like P1 and P2 actually define the data type which generates all possible terms of this data type of naturals, right. Okay, so, the third postulate essentially says that 0 should be distinct from any successor, okay, that 0 is not the same as any successor. So, these are completely syntactic forms, right. So, what we are saying is that whatever terms you can generate from P1 and P2, you cannot identify any of the terms generated from P2 with something in P1. If you were to take the theory of Booleans, for example, one explicit axiom you would require in any first order theory of Booleans, though we take it for granted, one explicit axiom you would require is that 0 is not the same as 1. If you do not have the axiom, then there are models for all your predicates on Boolean algebra, where there is a single carrier set and true is the same as false. So, unless you have this axiom that 0 is not equal to 1, you have not actually defined a Boolean algebra in its proper form. You have not defined a 2 element. So, that essentially says that your carrier set must have at least 2 elements. It could have more, of course, but that it is important to specify that 0 is not the same as 1. Yeah, after all, 0 and 1 could be different names for the same object, right. So, that possibility has to be excluded. Okay. The fourth axiom essentially says that your construction is deterministic. Yeah, and it also says that this successor function, the successor can be thought of either as a function or it can be thought of as a constructor, right. I mean at the time when Peano defined it, the notion of a constructor was not very well understood, since there was no programming and so on and so forth, no computers and so on and so forth. But what the only thing that you could relate to is the syntax of terms. So, all that this says is that this successor regarded as a function is an injective function. Okay. So, which means that if there are two objects, not x and y, not necessarily distinct from each other, and if I apply the successor function to each of them and I look at the resulting objects and they are the same object, then the original objects must have been the same. So this says that the successor function is essentially injective, right. Okay. And lastly, Peano had this. Okay, it's important here to think of it this way. So, let P be a property. The word property here is already ambiguous. Okay, it is not clear exactly what is meant by that, and Peano left it open. He himself was not very clear about it, okay, but he knew that it is important. It is necessary to have such a thing. If you have a property P that is true for 0 and the property P is preserved under the successor function, that is actually what your induction step does, right. It says that the successor function does not affect the property and the property is preserved under successor, which is also equivalent in algebraic terms to saying that you can push the successor inside the property inside the property itself, right. Then all the numbers that you have generated, all the terms that you have generated from P1 and P2 also satisfy that property, right. So, this is what his principle of induction was, yeah, which translated in first order. Okay, so let me I will talk about this a little later. So, this notion of a property, he left it ambiguous, but basically it was any property. And when you look at the first order theory of numbers, then this property essentially becomes a unary predicate expressible in first order logic, okay. And therefore, it does not include properties of numbers which might be properties of finite subsets of naturals, for example, yeah. Those would be second order properties. So, whereas Peano's original formulation left it ambiguous with the idea that it can be any order actually, it need not be first order, but the first order induction principle would have essentially a property P specified in first order logic on the theory of individuals, where the individuals are drawn from the data type generating natural numbers through the 0 and the successor operation, yeah. So, let us look at the theory of naturals. We will start with so essentially we start inspired by Peano and you sort of reformulate it into first order predicate calculus. So, the theory of so here I do not have induction, yeah, induction is something I am going to talk about later. So, the first thing is that okay, so the first two of Peano's postulates essentially give you the signature, right, and there is an equality also. So, we will assume first order predicate calculus with equality. So, there is an equality relation and there is a 0 and a successor function, yeah, plus 1. By the way, I have not written the sort of this. I should have written it as S arrow S, yeah. That will have to be corrected, yeah. Okay. The first of Peano's postulates essentially says that 0 is a natural number. Okay, there is something else we need. Okay, P3 that 0 is not the successor of any natural number is what this axiom says. So, for all x, this it is not true that the successor of x is equal to 0. Okay. The other axiom that it is injective is this, which is trivial, and then we need an axiom which says essentially that if a certain natural number is in successor form, then it does have a predecessor. Okay, and that is what this one says. If something is not equal to 0, then it does have a predecessor. Okay. This in conjunction with this injectivity property actually ensures that this predecessor is unique. Okay. But that will have to be proven. Okay. So, that is one thing that let us say that is the first thing you have to prove, that that predecessor whenever it exists is unique. Yeah. Okay. Then there is what we want from our theory of naturals is that the entire set of even though the entire set of naturals that we get a countable model. Okay. You should not have only finite models, because the set of natural numbers as we know it is infinite, is countably infinite. And so, in order to ensure that there is a countable model, you have to essentially say that no successor element, these are all distinct. This says that for any x, okay. So, now here this is an abbreviation. Are you able to distinguish the colors? So, this I have put +1 enclosed in black parenthesis and raised to a black n. Okay. The black indicates the meta language, right, it is an abbreviation. It is an abbreviation for an n-fold application of +1 for each n greater than 0, right. So, so essentially what we are saying is the green. So, I have phi +1 black n and green distinct, right. Okay. Now, this one essentially if I take n equals let us say 2, then this essentially stands for for all x I need purple of course, but okay, well, I will just live with 1 +1 +1 by the way there should be a not here, not oh god, for all x not x +1 +1 equal to x. Yeah. So, this for each value of n it is essentially an abbreviation for this, right. So, this n distinct. So, what we are saying is that for any x, any number of applications of successor to x cannot give you back x. Okay. And this is an infinite collection of axioms. There has to be an infinite collection of axioms, otherwise what you can it opens up the possibility of having finite models. Okay. In particular, some of the finite models which are very popular in number theory are these modulo n, yeah, for some appropriately chosen value of n, right. Okay. So, therefore, this theory of naturals which guarantees an infinite, which guarantees that there are only infinite models, consists of all these axioms. So, basically that 0 is not the successor of any element, the successor operation is injective, and if something is not equal to 0, then it must be the successor of some element, and for each n, successor applied n times to x is not equal to x for each x, yeah, for each x and for each n, successor, the nth successor of x cannot be equal to x, yeah. That guarantees essentially infinitary models. But there is something else. One of the things I did, let us go back, at some point okay, it must be here. Did we do the isomorphism lemma here? We spoke about the distinguishability of structures, right. Okay. We spoke about isomorphic structures, right. So, we said that isomorphic sigma structures cannot be distinguished by P1 sigma, right. So, if you look at our theory of naturals, there are at least two different models. The theory of even numbers is one model and the theory of odd numbers is another model, and the theory of the actual set of naturals is another model, yeah. They are all infinitary models which satisfy the axioms, which satisfy Peano's postulates, for example, yeah. And you can actually go further. I mean, you can just talk about 2 raised to n, for example. I mean, for each natural number n, take the set of all powers of 2, where your successor is the next higher power of 2. Yeah, I mean, so all these are isomorphic structures, and any statement that you make about the naturals is also true about these structures translated appropriately. Yeah, that was one thing. So, this distinguishability you cannot. So, basically first order logic cannot distinguish isomorphic structures. Basically isomorphic structures are different only in name, yeah, and there is an isomorphism which there is a name isomorphism which makes things, and in interpretation which makes them essentially the same. So, we had this isomorphism lemma which essentially said that first order logic is not powerful enough to distinguish isomorphic structures. Then we asked this question which we never answered: are there sigma structures which satisfy the same sigma formulae, but are not isomorphic? Okay. And now, let us get back to our theory of naturals. So, okay, let us just quickly go through this. X raised to plus 1 n denotes the n-fold application of plus 1 to x. Says that every non-zero element must have a predecessor, and this set of natural numbers under sigma s is a model of the axioms phi of s. The infinite collection of axioms is necessary to obtain models that are countably infinite. Yeah. The axioms phi plus 1 ensure that there are no finite models. Yeah. What you can do is, if you restrict this set of axioms phi of plus 1 n to supposing you restrict this to some instead of n greater than 0, you have 0 less than n less than m for some given m, then what you essentially get, you get both finite and infinite models, right. You get finite models like modulo m models, and modulo m is not the only model. You can even take modulo 2m and so on and so forth. Yeah, you get all those finite models, plus you do get infinite models. Now, if you want only finite models, which actually what happens if you have done a course on number theory in some systematic fashion, what you will notice is that at some point after Euclidean algorithm, it is much more convenient to deal with just modulo n structures, and usually that modulo n is that n is some prime. So, it is usually you do, or you try to reduce all your properties for large numbers from infinite sets to finite sets by doing a division modulo 5 modulo p for some prime p. This is very useful, and the whole of number theory becomes useful precisely because you can do that. There are a large number of models which are a large number of useful theorems, especially RSA for example, which allow you to move between modulo p structures and the whole of the naturals if you want, or the whole of the integers if you want. Yeah. Okay. But there is something else, coming back to our question. So, what is now, supposing you want only finite models, then you will have to add an extra axiom which says for some m, let us say, that the mth successor of x for all x is equal to x. So, then you will get all 0 to m minus 1. So, you will get modulo m structures, and then you will not get any infinite models, you get only finite models. But if you do not add this axiom, but you still restrict n to less than m, then you have both finite and infinite models. Yeah. Okay. Yeah. So, did somebody ask something? No. Okay. So, there is, so coming back to this question, what we can do even with the current thing is, so we have essentially constructed 0, and I do not want to keep writing plus 1 plus 1 plus 1 and so on and so forth. So, essentially we have constructed 0, 1, 2, 3 etc., the entire set n. Yeah. And now what we can do is, I take this, so this is my set n generated entirely by this by Peano's postulates 1 and 0 and 1, or 1 and 2. Yeah. There is nothing in those postulates and nothing in this axiomatization that we have done, which, let me see, this is 321. No? Okay. Go back to 541, let's say 540. So, between this, there is nothing which prevents me from adding a new fictitious element. I mean, this is a model that satisfies all these axioms. Yeah, there is nothing that prevents me from considering an n prime, okay, which consists of the whole of n, of course, and then I am going to add a new element, okay, and I am going to call this element, I am going to call it 0 prime. Yeah. Okay. Then what do? I look at all these axioms, and 0 prime is, and this thing allows me to generate successor of 0 prime, successor of 1 prime, yeah, and so on and so forth. Yeah. But that is not all, that is only from the process of generation from this successor function. It has to be a total. So, it should be possible to, if you add an element 0 prime, you should be able to generate successor of 0 prime, and if you have generated successor of 0 prime, then it has to be closed, right, on S. So, it is closed, but the problem is, here if 0 prime is distinct from 0, then this one says that it must be the successor of an element, it must have a predecessor. So, what it means is that now this axiom essentially says that I cannot stop with this, I have to start adding new elements. Let me call it -1 prime, and by the same token I would be generating -2 prime, -3 prime and so on and so forth. Okay. Now, consider n prime. N prime is a countable model of these axioms. There is absolutely no reason why I should stop there. I create an n double, and which is essentially going to be n prime union a new 0 double prime, and this is n prime essentially union a new actually I am generating all the integers, right, because of that. So, let me call that z double prime, right. The point is that the theory of naturals does not say that you should not generate the integers, does not say that you cannot generate two different copies of integers, right. The important thing, going back to this question, and what are we saying now? N prime, n double prime, n triple prime, whatever you might generate, they all have copies, distinct copies of the integers within them. And if I have an infinite number of different copies of the integers also, I still get only a countable model. Now, none of these models is isomorphic to each other. Right? There is no isomorphism between them, because clearly one n is a subset of n prime and n prime is a subset of n double prime and so on. There is no isomorphism that you can define. So, the notion of first order indistinguishability goes beyond the isomorphism lemma. There are also non-isomorphic structures which cannot be distinguished by first order form. So, these, and in fact what you can do is you take any expansion of the theory of numbers, all these models are called the non-standard models of arithmetic. Yeah. So, first order indistinguishability is limited, I mean first order distinguishability is limited, very limited. What we showed was that it cannot distinguish isomorphic structures, but what this shows is that there are also non-standard models that you can create which are not isomorphic to each other, or to what might be called a standard model. This is called a standard model. So, Peano's original assumption that he can generate all the naturals and exactly the naturals by his axioms is not true. I mean, you can generate things which are not isomorphic to the standard model too, and your first order logic will not be able to distinguish them. Every property that you prove for this theory, I am sorry, oh no, every property that you prove of the naturals would also be true in these non-standard models. Actually, the problem goes further. The problem goes further in the sense that there are people who, I mean, this was the the existence of non-standard models came probably in 1920s or 30s, right. But after that there are people who actually created non-standard analysis. So, the entire theory of real analysis or complex analysis, you can create non-standard models for all those axioms. I mean, so that is by the way, even if your mathematics textbooks do not explicitly say so, most of the time all your mathematics textbooks are using some form of using first order reasoning applied to higher order logic, because most of those axioms of first order logic are also applicable in higher order logic. The differences will come in terms of decidability and so on and so forth, finiteness and infiniteness, but otherwise whatever you so all your presentations of things in analysis like Dedekind cuts or the construction of reals, the construction of rationals and so on and so forth, what you can do is you can start with so basically you can start with the naturals and create fractions, create integers and then create reals through Dedekind cuts. But now I can take these non-standard models and do the whole thing. I mean, it is very reminiscent of that thing of there is the ancient Indian mythological story of the sage Vishwamitra constructing a new universe. He started constructing a new universe, that is like constructing a non-standard model of the existing axioms of Brahma, right. Okay. So, so you can actually create non-standard analysis, and there are very many different kinds of non-standard analysis possible, and those have been created. Yeah. So, notions of continuity, which the whole purpose of analysis was to formalize Newton's assumptions about continuity in some logical framework, right, and that those acquire new meanings when you create non-standard analysis, non-standard Dedekind cuts, non-standard real numbers from using higher order logics from the naturals, right. And of course, my purpose was basically to go through just the standard model, but to show that there do exist non-standard models, to show that first order logic is not expressive enough for many properties, but most of our reasoning still is first order. What we do is we use the same reasoning mechanisms of first order when we go into higher orders, because the reasoning mechanisms of first order are fairly general. In any higher order logic, your propositional connectives have the same kinds of meaning, right, and your existential and universal quantifiers also have the same kind of meaning. You have to instantiate them. You have to instantiate them and you have to generalize them. So, the axioms of higher order logic will also be the same, but we keep transcending these borders. Yeah. Okay, so I will stop here and we will do more about Presburger arithmetic and piano arithmetic next time. Yeah.